In 1982, in a basement laboratory at the Institut d'Optique in Orsay, France, a 35-year-old physicist named Alain watched a number appear on his detector readout that should not have been possible. The number was 2.697. The margin of error was plus or minus 0.015, and the maximum value the universe was supposed to allow, if reality works the way every physicist since Newton assumed it does, was 2. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon. Links in the description. That number, 2.697, was not a marginal violation. It was not a statistical flicker. It was 40 standard deviations above the limit. To give you a sense of how definitive that is, the discovery of the Higgs boson at CERN in 2012, the result that made front-page news in every country on Earth and won a Nobel Prize within 18 months, that was 5 standard deviations. 5 sigma is the gold standard in particle physics, the threshold beyond which you are allowed to claim a discovery. Aspect's result was 40 sigma, 8 times more statistically certain than the discovery of the Higgs boson. And almost nobody, outside a handful of quantum optics labs, heard about it. The result was not classified. It was not suppressed in any formal sense. It was published in Physical Review Letters, one of the most prestigious journals in physics. But the physics community treated it the way you might treat a medical test result you do not want to read. They acknowledged it existed. They did not discuss what it meant. What Aspect had tested was something called Bell's inequality. What he had proven was that the universe is not locally real. And if that phrase does not immediately unsettle you, it is because nobody has ever explained to you what it actually means. It means that at least one of 2 things you have believed your entire life is experimentally, definitively false. Either objects do not have definite properties when nobody is looking at them, or distant parts of the universe can influence each other instantaneously, with no signal, no delay, no mechanism, across any distance. Those are not fringe possibilities. Those are the only 2 options the math leaves you. And there is a third escape route, but it is worse than both of those combined, and we will get to it. I have been obsessed with Bell's theorem since I first encountered it years ago, and the thing that drew me in was not the physics itself, although the physics is extraordinary. It was the gap between the magnitude of the result and the public's awareness of it. This is not some speculative hypothesis about dark matter or string theory that might be confirmed someday. This is an experimental fact, confirmed with a certainty that dwarfs almost every other result in modern physics, and it has direct, undeniable implications for the nature of reality. And yet, if you stopped 100 people on the street and asked them what Bell's theorem is, 99 of them would have no idea what you are talking about. I have spent more time on this topic than probably anything else this channel has covered. I have read the original papers. I have read Aspect's own first-person account of designing the experiment. I have read Bell's 1964 paper so many times I can practically recite the algebra. And what I keep coming back to is this. The result was confirmed. It was published. It was verified by every subsequent experiment for the next 4 decades. And the physics community responded by collectively looking the other way, not because the result was wrong, because the result was too disturbing to talk about. And here is the part that should bother you. Every attempt to escape this result, every loophole, every alternative explanation, every clever theoretical workaround that physicists have proposed over the last 43 years Every single one of them has been tested and closed. The escape routes do not lead out. They lead deeper. The last remaining exit requires you to accept that your choice to watch this video right now, the movement of your finger on the screen, the firing of the specific neurons in your brain that made you click, all of it was determined at the moment of the Big Bang, 13.8 billion years ago. That is not metaphor. That is not poetic exaggeration. That is the actual physics. One of the three assumptions underlying Bell's theorem is that experimenters can freely choose what to measure. If that assumption is wrong, if your choices were predetermined by the initial conditions of the universe, then Bell's inequality need not be violated, and local realism can be saved. But the cost is everything you have ever experienced as choice, deliberation, or agency. That is the trade, free will for a locally real universe. And most physicists think the price is too high. But this story does not start in Orsay in 1982. It starts almost 50 years earlier with the most famous physicist in history picking a fight he was sure he could win. Princeton, New Jersey, 1935. Albert Einstein was 56 years old, and he was angry. Not the loud, dramatic anger of a young man, the cold, precise, mathematical anger of someone who had spent a decade watching a theory he helped create being interpreted in ways he found philosophically monstrous. The theory was quantum mechanics. Einstein had been one of its founding architects. His 1905 paper on the photoelectric effect, the one that actually won him the Nobel Prize, had introduced the idea that light comes in discrete packets called quanta. He had been there at the beginning, and now he was watching Niels Bohr and the Copenhagen School take the theory in a direction that Einstein believed was not just wrong, but dangerous. The argument was about completeness. Bohr and his followers claimed that quantum mechanics was the full description of reality, that when quantum mechanics says a particle does not have a definite position until you measure it, that is not a limitation of our knowledge. That is a statement about reality itself. The particle genuinely does not have a position. It exists in a superposition of all possible positions, and only the act of measurement forces it to choose. Einstein thought this was insane, and I personally think his objection was sharper than most textbooks give him credit for. He did not object to the math. He objected to the interpretation. His position was subtle, and it was precise. He believed that if measuring one particle instantly determines the state of another particle on the other side of the universe, and if we accept that no signal can travel faster than light, then the particle on the other side must have had a definite state all along. It was not created by the distant measurement. It was revealed by it. The information was always there, encoded in some deeper layer of reality that quantum mechanics simply does not capture. This was not the first round of the Bohr-Einstein debate. The two had been clashing since the Fifth Solvay Conference in 1927, where Einstein proposed thought experiments designed to defeat the uncertainty principle, and Bohr spent sleepless nights constructing counter-arguments. At the Sixth Solvay Conference in 1930, Einstein thought he had a killer argument involving a photon box that seemed to violate the energy-time uncertainty relation. Bohr reportedly stayed up the entire night. The next morning he showed that Einstein's own general relativity, specifically the gravitational redshift, actually saved the uncertainty principle. Einstein conceded the point, but shifted his attack. By 1935, he was no longer trying to defeat quantum mechanics from the outside. He was trying to show it was incomplete from within. In May of that year, Einstein published the argument as a paper in Physical Review with Boris Podolsky and Nathan Rosen. The paper was called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And it is now universally known as the EPR paper. The paper introduced a criterion of reality that sounds almost self-evident. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. In plain language, if you can predict a measurement outcome with certainty without touching the system, then the thing you predicted must have been real before you predicted it. This seems like common sense. It is precisely the common sense that quantum mechanics violates. The argument went like this. Take two particles that interact briefly and then fly apart. Quantum mechanics says they become entangled, meaning their properties are correlated no matter how far apart they travel. This is not a metaphorical correlation. It is not that the particles are similar the way twins are similar. It is a specific mathematical relationship in which the quantum state of the pair cannot be written as a product of individual quantum states. The pair has properties that neither particle possesses individually. The particles are, in a precise and measurable sense, not separate things. They are one system, described by one quantum state, no matter how far apart they travel. Measure the position of particle 1, and you instantly know the position of particle 2. But you could instead have measured the momentum of particle 1, and then you would instantly know the momentum of particle 2. By the locality principle, measuring particle 1 cannot possibly affect particle 2 if they are far enough apart. So particle 2 must have had both a definite position and a definite momentum all along. But the uncertainty principle says no particle can have both simultaneously. Therefore, quantum mechanics is incomplete. There must be hidden variables, deeper properties we have not discovered yet, that determine the outcomes in advance. It was elegant, it was logical, and Einstein was furious that Podolsky had written the text without consulting him and then leaked the paper to the New York Times before publication. The Times ran the headline, "Einstein attacks quantum theory." Einstein complained to Erwin Schrödinger in a letter dated June 19, 1935, that the essential point had been smothered by the formalism. And here is where most people get Einstein wrong. And getting this right matters because it changes the entire framing of what came after. Einstein was not a curmudgeon who refused to accept the new physics. He was not clinging to a classical worldview out of stubbornness. He understood quantum mechanics deeply. He had helped create it. What he objected to was not the mathematics, but the claim that the mathematics was the complete picture. His essential point, the one Podolsky had buried under formalism, was about locality. If measuring one particle can instantly change the physical state of a distant particle, and if you accept special relativity's prohibition on faster-than-light influences, then something is wrong. Either the distant particle already had its state, and quantum mechanics just does not describe it, or you are accepting what Einstein called "spookhafte Fernwirkung," spooky action at a distance. That phrase, by the way, did not come from the EPR paper. It came from a private letter Einstein wrote to Max Born in March of 1947, published decades later in the Born-Einstein letters. And it was not a casual expression of wonder. It was an expression of horror. Einstein believed that if physics requires spooky action at a distance, then physics has failed. Einstein chose the first option. He believed in hidden variables. The universe was locally realistic, and quantum mechanics was a statistical approximation of a deeper deterministic theory. He spent the last 20 years of his life looking for that deeper theory. Abraham Pais, his colleague at Princeton, recorded a moment that captures the depth of Einstein's conviction. They were walking together one evening, and Einstein stopped and asked, "Do you really believe the moon exists only when you look at it?" The question was not rhetorical. He never found the deeper theory, and 30 years after his death, a man working on it during his holidays would prove that it does not exist. Bohr responded to the EPR paper almost immediately with a paper of his own, same journal, same title. His argument was dense, elliptical, and honestly, I have read it 4 times and I am still not entirely sure I grasp what he was claiming. The physics community has debated Bohr's response for nearly 90 years. What most scholars agree on is that Bohr argued you cannot talk about the properties of a particle independent of the measurement context. The experimental arrangements required to measure position and momentum are physically incompatible. Complementary, you have to pick one. And once you pick, you define the very conditions under which any prediction makes sense. He wrote of an influence on the very conditions which define the possible types of predictions. Many physicists find this response obscure. Some argue it does not actually engage with Einstein's locality concern at all. The physics community declared Bohr the winner anyway. This was not because Bohr's argument was clearer or more persuasive. It was because quantum mechanics worked. It predicted experiments correctly to extraordinary precision. Why argue about interpretations when the math keeps working? A culture developed in physics departments worldwide that would persist for the next 3 decades. The attitude was captured by a phrase coined by N. David Mermin of Cornell in a 1989 Physics Today column. Shut up and calculate. If you question the foundations of quantum mechanics, you are not doing physics, you are doing philosophy. And philosophy does not get you a tenured position. The irony is that the phrase is widely misattributed to Richard Feynman. Mermin actually investigated this in a follow-up column in 2004 and found no evidence Feynman ever said it, but it captured something real about how the profession policed itself. Mermin traced the attitude to his own graduate training at Harvard in the late 1950s, where professors explicitly warned him, "You will never get a PhD if you allow yourself to be distracted by such frivolities." And the frivolities in question were things like, what does the wave function represent? Is there a real world independent of observation? And what happens during a measurement? These are not frivolous questions. They are arguably the most important questions in all of physics, and for decades, asking them was professional suicide. I think about this a lot. There is a tendency to tell the history of science as a march of progress, where each generation builds on the last and the truth gradually emerges. But the reality is messier and uglier. Sometimes the profession collectively decides that a question is off limits, not because the question is bad, but because the answer is too uncomfortable. And the people who insist on asking anyway pay for it with their careers. What nobody knew in 1935 was that the EPR argument contained a hidden assumption that nobody had identified. An assumption so deeply embedded in the way human beings think about the world that it took nearly 30 years for a single physicist to see it. And when he did, working on it in his spare time during holidays from his real job designing particle accelerators, he would prove that Einstein's escape route was not just unlikely, it was mathematically impossible. That physicist was John Stuart Bell, and the proof he found would turn out to be the most profound result in the history of physics. Bell was born on July 28, 1928, in Belfast, Northern Ireland. His father was a horse trader. His mother, Annie, was a dressmaker. He had an older sister, Ruby, and two younger brothers, David and Robert. None of his siblings stayed in school past the age of 14. The family could not afford it. Only John continued, and the path was not easy. He could not afford the grammar school, so he attended Belfast Technical High School, which was not the typical pipeline to a career in theoretical physics. His mother sewed his academic gown from wartime blackout curtains. At the age of 11, he told his family he wanted to be a scientist. They called him the Prof. He graduated at 16 and took a job as a laboratory assistant at Queen's University Belfast. Because the family needed the income, this was supposed to be the end of his academic career. But two professors, Carl Emilius and Robert Sloan, noticed something about the quiet teenager cleaning their equipment. They let him attend lectures. They encouraged him, and Bell earned 2 first-class honors degrees, one in experimental physics in 1948 and one in mathematical physics in 1949. From a working-class family in Belfast to 2 firsts at Queen's. That trajectory alone would have been a remarkable story. It was not even the beginning. He went to work at the UK Atomic Energy Research Establishment at Harwell, married a fellow physicist named Mary Ross, and in 1960 moved to CERN in Geneva, where he would spend the rest of his career. His day job was designing particle accelerators. He was good at it. His most cited work in high-energy physics was the Bell-Jackie-Adler anomaly of 1969, which solved the problem of neutral pion decay. This was serious, respected, mainstream physics. Bell was not a fringe figure. He was a well-regarded accelerator physicist who happened to have a secret intellectual life. Quantum foundations was his hobby. He pursued it, as he put it, in evenings and on holidays. He did not discuss it openly with his CERN colleagues. He kept it separate, almost hidden, because the culture of his profession had made the question professionally radioactive. There is a tension in Bell's career that I find deeply revealing. By day, he was using quantum field theory to design accelerator components, trusting the math completely, relying on it to predict what would happen when particles collided at enormous energies. By night and on weekends, he was asking what that math actually means, whether the objects it describes are real, whether the predictions it makes tell you anything about what exists when you are not measuring. Most of his colleagues saw no contradiction. The math works. Why ask more? Bell could not accept that answer. He once said that the founding fathers of quantum mechanics were right to feel uneasy, and that the problem they could not solve has not been solved by their successors. And the thing that set him on this path was something he read in 1952, something that, according to the physics establishment, should not have existed. In 1932, the Hungarian mathematician John von Neumann had published a proof in his book Mathematical Foundations of Quantum Mechanics that purported to show hidden variable theories were impossible, not just difficult, not just unlikely, logically impossible. Von Neumann was one of the most brilliant mathematicians of the 20th century, and his proof carried enormous weight. For 20 years, it was treated as gospel. If anyone suggested that particles might have definite properties determined by hidden variables, the response was simple. Von Neumann proved that cannot work. Move on. Then David Bohm published 2 papers in Physical Review in 1952, and blew the whole thing open. David Joseph Bohm was born in 1917 in Wilkes-Barre, Pennsylvania, to a Hungarian Jewish immigrant father who ran a furniture store. He studied physics at Penn State and then at Berkeley under Robert Oppenheimer. He was brilliant, passionate, and politically active in ways that would soon destroy his career. He joined the Young Communist League. He attended meetings of the Committee for Peace Mobilization. During World War II, General Leslie Groves denied Bohm's security clearance for the Manhattan Project at Los Alamos. And here is the absurdity that makes you want to scream. Bohm's doctoral research on scattering calculations turned out to be useful to the Bohm project and was immediately classified. He could not access his own thesis. He could not read the work he had done. Oppenheimer had to personally certify that Bohm had completed the research so he could receive his PhD based on work he was no longer allowed to see. After the war, Bohm got a position at Princeton and worked closely with Einstein. The two had long conversations about quantum mechanics, locality, and the nature of reality. Bohm's 1951 textbook, Quantum Theory, presented the Copenhagen interpretation so clearly and so thoroughly that the exercise of writing it convinced him something else was possible. Then, McCarthy came for him. In 1949, the House Un-American Activities Committee called Bohm to testify about his political associations. He invoked the Fifth Amendment. In 1950, he was arrested for contempt of Congress. He was acquitted in 1951, but Princeton had already suspended him. The university president, Harold Dodds, refused to renew his contract. And Oppenheimer, Bohm's own doctoral advisor, the man who had certified his PhD, opposed his appointment at the Institute for Advanced Study and advised his former student to leave the country. Think about that for a second. The man who mentored him, who signed off on his degree, told him to flee. Bohm left for the University of Sao Paulo in Brazil. The US consulate confiscated his passport. He was, for all practical purposes, a political exile, trapped in a country where he had no roots and no community. And this, weirdly, freed him. He later said the exile liberated him. He was able to think more easily and more freely without having to speak the language of other people. There is something I find almost unbearably poignant about this part of the story. The chain of events that leads from Bell's theorem to the most profound experimental result in physics passes directly through McCarthyism. If the US government had not persecuted Bohm for his political beliefs, he might have stayed at Princeton, might have continued working comfortably within the establishment, might never have had the intellectual freedom to challenge the Copenhagen interpretation. His exile, his isolation, his separation from the mainstream, that is what gave him the space to think the unthinkable. And his 1952 papers, written in involuntary exile, are the direct spark that ignited Bell's theorem 12 years later. Without McCarthyism driving Bohm from Princeton, Bell's theorem might never have been formulated. The most important result in the foundations of physics may owe its existence to one of the ugliest episodes in American political history. In 1952, from Sao Paulo, Bohm published his pilot wave theory in 2 papers in Physical Review. The theory revived and extended an idea that Louis de Broglie had proposed at the 5th Solvay Conference in 1927, where it had been shot down by Wolfgang Pauli. De Broglie abandoned it. Bohm, 25 years later, and an ocean away, brought it back to life. The mechanics are elegant, Particles have definite positions at all times. That is the realism part. They are guided by a pilot wave, which is mathematically identical to the quantum wave function, but treated as a real physical field rather than a probability tool. The particle serves the wave. The wave determines the particle's velocity through a guidance equation. The theory is fully deterministic. If you know the initial positions of all particles and the wave function, you can predict everything with certainty. There is no randomness at the fundamental level. The apparent randomness of quantum mechanics arises because we do not and cannot know the exact initial positions. The probability distribution in Bohm's theory is identical to the Born rule of standard quantum mechanics, not as a postulate, but as a consequence of the dynamics. It reproduces all the predictions of standard quantum mechanics exactly. Every experiment that confirms quantum mechanics also confirms Bohm's theory. The two are empirically indistinguishable, every single one. The double-slit experiment, the EPR correlations, the violation of Bell's inequality, quantum tunneling, the stability of atoms, all of it. The theory does not disagree with any measurement that has ever been performed, but there was a catch, and the catch was the entire point. Bohm's theory is explicitly, unapologetically non-local. The velocity of any particle depends on the positions of all other particles in the universe, instantaneously, regardless of distance. The pilot wave connects everything to everything else. If you measure a particle in Paris, the pilot wave changes the trajectory of its entangled partner in Tokyo in 0 time. Not approximately 0, exactly 0. The physics establishment reacted to Bohm's theory with something between contempt and rage. Oppenheimer reportedly said that if we cannot disprove Bohm's theory, we should agree to ignore it. Pauli called it artificial metaphysics. The theory made the same predictions as standard quantum mechanics, so it was seen as superfluous at best and misleading at worst. And von Neumann had supposedly proved hidden variable theories were impossible. So there must be something wrong with Bohm's construction. There was not. There was something wrong with von Neumann's proof. A German mathematician named Greta Hermann had actually identified the flaw as early as 1935, but her work was completely ignored because she was a woman publishing in a field dominated by men who did not read her journals. Von Neumann's proof contained a hidden assumption that amounted to assuming the conclusion. He assumed that the expectation value of the sum of two observables equals the sum of their expectation values, even for observables that cannot be measured simultaneously. This sounds technical, and it is, but the point is straightforward. The assumption has no justification for incompatible observables. It is not a law of nature. It is a mathematical convenience that von Neumann elevated to a physical principle, and it is precisely the kind of assumption that hidden variable theories violate. Bell later described von Neumann's proof, and I love this quote so much. He said it was not merely false but silly. You may quote me on that. Bohm moved to Israel in 1955, then to Bristol in 1957, then to Birkbeck College at the University of London in 1961, where he stayed until retirement. With Yakir Aharonov in 1959, he discovered the Aharonov-Bohm effect, showing that electromagnetic potentials have real physical consequences even in regions where the fields themselves are zero. A charged particle passing through such a region acquires a measurable phase shift. This was genuinely shocking because it meant potentials, which most physicists treated as mathematical fiction, are physically real. Another moment of Bohm seeing something deeper in the formalism than the establishment wanted to acknowledge. He did not recover US citizenship until 1986, after a lawsuit. He died on October 27, 1992, of a heart attack in a London taxi. So Bell read Bohm, and Bell had his question. Bohm had shown that hidden variable theories were possible, despite von Neumann. But Bohm's theory had this conspicuous non-locality. Every part of the universe is connected to every other part instantaneously. Was this a defect of Bohm's particular construction? Could someone build a local hidden variable theory that reproduced quantum predictions? Could you keep Einstein's locality and still have particles with definite properties? Bell produced 2 papers during his 1963-64 sabbatical at Stanford, Wisconsin, and Brandeis. The first, written first but published later in Reviews of Modern Physics in 1966, was the demolition of von Neumann's proof. Bell identified the exact hidden assumption and showed why it was unjustified. That paper cleared the ground. The second paper asked the deeper question. Bell later wrote that in 1952, he saw the impossible done. If the impossible was possible, if Bohm could build a working hidden variable theory, despite von Neumann's supposed proof, then the question became whether nature itself imposed a constraint that von Neumann's flawed argument had failed to identify correctly. And what he found was devastating. You cannot build a local hidden variable theory that reproduces the predictions of quantum mechanics. It is not that nobody has managed it yet. It is not that the problem is really hard. It is that the predictions of quantum mechanics are logically inconsistent with the assumptions of locality and realism combined. Any theory that assumes particles have definite properties determined by local hidden variables must obey a mathematical inequality. Quantum mechanics violates that inequality, not marginally, decisively, and the violation can be tested in a laboratory. The argument is beautiful in its simplicity, and I want to explain it properly, because I think the logic is accessible to anyone willing to follow a few steps of reasoning. Imagine 2 particles created together in a special state called the singlet state, and sent to detectors far apart. Each detector can be set to one of several orientations, like rotating a polarizer to different angles. The particles hit the detectors and each gives a result either +1 or -1. Now, if the particles have pre-existing properties that determine their outcomes, think of it as each particle carrying a hidden instruction sheet that says what to do for each possible detector setting. And if the detector settings cannot influence each other because they are too far apart for any signal to travel between them in time, then the correlations between the results at the 2 detectors must obey a specific mathematical limit. The key insight, the thing Bell saw that nobody else had seen in 30 years, is that different detector settings create different correlations, and the way those correlations combine is constrained by the assumption of locality. If you only look at one pair of settings, you cannot distinguish quantum mechanics from local hidden variables. The correlations look the same, but when you combine correlations from multiple pairs of settings, the constraints become visible. Local hidden variables cannot produce enough correlation at all angles simultaneously. They have to compromise. Quantum mechanics does not. Let me try to make this concrete, because the intuition matters as much as the math. Imagine you and a friend are in separate rooms. Before you were separated, you were both given envelopes, and someone prepared those envelopes in advance. You and your friend will each open your envelopes and find a card with either a plus sign or a minus sign. The person who prepared the envelopes could have put any combination in: plus plus, plus minus, minus plus minus minus. The content is fixed in advance. Local realism says the envelopes are like this. Whatever answer you get was determined when the envelopes were prepared, and opening your envelope cannot change what is in your friend's envelope. Now here is the problem. If you and your friend each have a choice of which envelope to open, and there are multiple envelopes prepared for different questions, the correlations between your answers across all possible questions are constrained. There is a ceiling on how correlated your answers can be, because the answers were all fixed in advance, and each envelope has to commit to a specific answer for each specific question. That ceiling is S equals 2. It is a mathematical limit that any pre-assigned instruction sheet must obey. Quantum mechanics says the particles do not have instruction sheets. The answers are not fixed in advance. And because they are not fixed, the correlations can be stronger than any instruction sheet could produce. The particles can be more coordinated than is possible if they had predetermined answers. That is what S equals 2.828 means. The universe is more correlated than classical logic allows. And the only way to exceed the classical limit is if the answers are not predetermined, or if the particles are communicating, or if the questions were not freely chosen. Those are Bell's 3 assumptions, and at least one of them must be wrong. The version that matters most for experiments is called the CHSH inequality, named for John Clauser, Michael Horn, Abner Shimony, and Richard Holt, who derived it in 1969. Take 4 measurements, each a combination of 2 different detector settings on each side. Combine the correlations into a single parameter, S. If local realism is true, S cannot exceed 2. That is the ceiling. That is the absolute maximum that any locally realistic universe can produce. Quantum mechanics predicts that S can reach 2 times the square root of 2, which is approximately 2.828. Not 2, 2.828. That is not close to the boundary. It is 40% above it, and the optimal detector angles to achieve this maximum are 0 degrees, 22.5 degrees, 45 degrees, and 67.5 degrees. In 1980, Boris Cyrelson proved that 2 times the square root of 2 is not just a prediction, but the absolute maximum that quantum mechanics can achieve. It is called the Cyrelson bound. But here is something that should make you think. The algebraic maximum of S is 4. You could imagine theories where S reaches 4. Such theories exist mathematically. They are called no-signaling theories because they respect the rule that you cannot send information faster than light, but they allow even stronger correlations than quantum mechanics. The Popescu-Rawlik box, proposed in 1994, is a hypothetical device that achieves S equals 4. So the hierarchy goes like this. Local realism allows S up to 2. Quantum mechanics allows S up to approximately 2.828. General no-signaling theories allow S up to 4. Quantum mechanics sits in the middle, which is deeply strange if you stop and think about it. It is more non-local than classical physics, but it is less non-local than it could be while still obeying special relativity. Why? Why does nature stop at 2 root 2 and not go all the way to 4? What physical principle sets the boundary? Nobody knows. This is sometimes called the Cyrelson question, and it is one of the deepest open problems in the foundations of physics. Something is constraining how non-local the universe is allowed to be. We can measure the constraint. We can calculate it. We cannot explain it. The universe has a speed limit for light and what appears to be a non-locality limit for correlations. And both limits are mathematically precise. And we understand one of them, special relativity. And we have absolutely no idea what enforces the other. Bell published his proof on November 4th, 1964, in a journal called Physics, Physique, Physica. It was a trilingual journal, published in English, French, and Russian. It had no page charges. In fact, it paid Bell a small fee for the paper. The journal folded after a few issues. Bell's paper accumulated fewer than a dozen citations in its first 6 years. The most important result in the foundations of physics appeared in an obscure journal that no longer exists, written by a man whose day job was designing accelerator magnets. I personally think this is the most underrated part of the entire story. Not the physics, the sociology. The most profound theorem in the history of science was published as a hobby project in a dead journal. And the man who wrote it had to hide his interest in foundational questions from his colleagues because the profession had decided that asking what quantum mechanics means was not real physics. And now someone had to actually test it. The mathematics said local realism should be violated. But mathematics and reality are not the same thing. You have to go into a laboratory, build the apparatus, generate the photons, rotate the polarizers, count the coincidences, and see what the universe actually does. The physics community wanted nothing to do with it. A young physicist named John Clauser saw the opening and walked through it. The warning he received from the establishment was the same one Bell had been living with for years. You will be wasting your career. John Francis Clauser was born on December 1st, 1942, in Pasadena, California. His father was Francis Clauser, a professor of aeronautical engineering at Caltech. His uncle was Edwin Macmillan, who won the Nobel Prize in Chemistry in 1951. Physics was in the family, but not this kind of physics. Clauser discovered Bell's paper while he was a graduate student at Columbia in the late 1960s, and he became instantly obsessed. He described the moment as transformative. Here was a mathematical proof that you could actually test whether the universe was locally real, and nobody was bothering to test it. His professors told him not to do it. The subject was considered professionally disreputable. Testing the foundations of quantum mechanics was not real physics. It was philosophy, and philosophy did not lead to grants, positions, or respect. Clauser pushed forward anyway. He co-authored the CHSH paper in 1969 while still a student, deriving the experimentally testable version of Bell's inequality that would make everything that followed possible. And here is a detail that I find remarkable. Clauser actually expected the experiment to confirm local realism and disprove quantum mechanics. He thought Einstein was right. He wanted hidden variables to win. He designed and built the experiment, hoping to prove Bell's inequality was respected, not violated. The fact that he ran the experiment, despite his own expectations, and then accepted the result when it contradicted his beliefs, tells you everything about the kind of scientist he was. He let the universe answer, and respected the answer even when it was not the one he wanted. In 1971, Clauser moved to UC Berkeley's Lawrence Berkeley Laboratory. With a graduate student named Stuart Friedman, he set up the first experimental test of Bell's inequality in a sub-basement room of Burge Hall. They had essentially no funding, They built the apparatus from scrounged parts and leftover equipment. The photon source was a calcium atomic cascade that produced entangled photon pairs, one green and one violet, emitted when calcium atoms were excited by ultraviolet light from an arc lamp. The polarizers were single-channel pile of plates devices. The whole setup was, by the standards of precision optics, held together with spit and tape. Clauser later joked that it looked like something designed by Rube Goldberg. They collected data for 200 hours. 200 hours of watching counters tick. 200 hours of checking alignments, maintaining the arc lamp, dealing with the 1,000 small failures that plague any precision experiment built on a shoestring. And the thing that makes this story remarkable is that Clauser did not know what to hope for. He had designed the experiment expecting quantum mechanics to fail. He wanted Einstein to be right. He wanted the universe to be locally real. So every hour of data collection was a kind of slow-motion confrontation with the possibility that reality is not what he thought it was. That takes a specific kind of courage, not the courage of the person who charges into battle knowing they are right, the courage of the person who builds the machine that might destroy their own beliefs and turns it on anyway. The result was a parameter S equal to 0.300 plus or minus 0.008. The local realist bound was 0.250. The violation was 6.3 standard deviations. That is the Friedmann-Clauser experiment, published in Physical Review Letters, Volume 28, in 1972. The first experimental proof that local hidden variable theories are wrong. And no, I am not making that up. About what happened next, John Clauser personally described it in multiple interviews. He went to Caltech to discuss his results with Richard Feynman, arguably the most famous physicist alive at that time. Feynman's response was to become, in Clauser's words, highly offended by his impertinent effort. Feynman insisted that testing quantum mechanics was tantamount to professing a disbelief in it, that quantum mechanics is obviously correct and needs no further testing. And he more or less threw Clauser out of his office. Other physicists gave similar responses. Nice experiment, now stop wasting time and money and go do some real physics. Clauser never held a tenured professorship. The experiment that first proved the universe is not locally real effectively ended his conventional academic career. Meanwhile, a competing experiment at Harvard by Richard Holt and Francis Pipkin initially appeared to support local realism, disagreeing with quantum mechanics by nearly 4 standard deviations. For a brief, confusing period in the mid-70s, there was genuine doubt about which side the evidence favored. Clauser repeated the Holt-Pipkin experiment in 1976 using a different mercury isotope and discovered that the anomalous result was caused by stressed Pyrex glass introducing erroneous polarization readings. An independent experiment by Edward Fry and Randall Thompson at Texas A&M confirmed quantum mechanics in just 80 minutes of data collection. The Holt-Pipkin paper was never formally published, but Clauser's experiment, decisive as it was, had loopholes. The polarizer settings were fixed in advance, before the photons were emitted. In principle, some unknown subliminal signal could have communicated between the detectors and the source, coordinating the results. Bell himself had specifically called for experiments in which the settings are changed during the flight of the particles. What was needed was someone willing to spend years building an apparatus that could switch detector settings faster than light could travel between them. That brings us back to Alain Aspect, and the story of how he ended up in that laboratory in Orsay is, I think, one of the best stories in the history of experimental physics. Aspect was born on June 15, 1947, in Agen, a small city in southwestern France. After finishing his master's thesis on holography, he went to Cameroon for his civil service, choosing to teach rather than serve in the military. While there, he bought the textbook by Cohen Tanuji, Diu, and Lalo, and taught himself quantum physics properly. He has said publicly that his university quantum mechanics course was, and I am paraphrasing him here, very bad teaching. He learned the real subject from a book, In Africa, on his own. When he returned to France in 1974, he obtained a permanent position as maître assistant at École Normale Supérieure de Cachan. This is the critical detail. In the French academic system, this was a tenured position, obtained without a PhD. He then went looking for a thesis topic, visiting laboratories and asking for interesting problems. He was given a file at Institut d'Optique that contained Bell's 1964 paper. He read it in about an hour. He has described the experience as love at first sight. After that 1 hour, he knew he wanted to devote his thesis to testing Bell's inequality. In 1975, Aspect traveled to CERN to meet Bell. The meeting has become legendary in the physics community, and Aspect has told the story so many times that the words are precise. He was very impressed to meet Bell, who looked very serious. Bell sat in silence while Aspect explained his experimental idea. And then Bell asked his first question. "Do you have a permanent position, young man?" Aspect said yes. He explained the French system, the tenured position, without a PhD. Bell replied, "Okay, very good. Let us talk science." Aspect asked why Bell had wanted to know about his job security. Bell explained that a majority of physicists would consider him a crackpot for doing this work. A majority, not a fringe minority of old guard traditionalists. A majority of working physicists in 1975 would have considered you professionally deranged for experimentally testing the foundations of quantum mechanics. Bell then strongly encouraged him, making clear he considered variable analyzers, the ability to change detector settings during photon flight, a fundamental improvement over Clauser's static experiments. There is a wonderful detail from this meeting. When Aspect proudly asked if he could keep his experimental scheme confidential, worrying a competitor might steal the idea, Bell responded, "Young man, we are doing basic research." The implication was clear. This was not about priority or credit. This was about answering a question that mattered. Aspect spent approximately 5 years designing and building his apparatus. His innovation was the photon source. He used a calcium-40 atomic cascade, exciting the atoms with 2 lasers simultaneously, a krypton-ion laser at 406 nanometers and a tunable dye laser at 581 nanometers. The cascade produced entangled photon pairs at wavelengths 551.3 nanometers, green, and 422.7 nanometers, violet, with the intermediate state having a lifetime of about 5 nanoseconds. 2 feedback loops maintained stability better than 0.5% over several hours. The production rate was staggering, 40 to 50 million entangled pairs per second. Where Clauser needed 200 hours to get his result, Aspect could achieve 1% statistical accuracy in 100 seconds. The first experiment was published in August 1981 with Philippe Grangier and Gerard Roger. Single-channel polarizers, the violation was 9 standard deviations. Clean, unambiguous, in excellent agreement with quantum mechanical predictions. The polarizers were separated by 6.5 meters, about 4 coherence lengths, which also refuted Furry's 1936 hypothesis that entanglement would vanish beyond the coherence length. It does not. The second experiment came in July 1982. This was the breakthrough. Aspect used 2-channel polarizing cubes that transmitted one polarization and reflected the orthogonal one, making it a true optical analog of a Stern-Gerlach device for the first time in the history of Bell tests. 4 coincidence circuits counted all 4 possible outcome combinations simultaneously. The polarizer angles were set at the optimal Bell test values 22.5 degrees apart. The result was S equals 2.697, plus or minus 0.015, a violation of the CHSH bound of 2 by more than 40 standard deviations. Aspect later said the number was closer to 50 sigma. This was 83% of the maximum possible quantum violation. The polarizers were separated by 13 meters. But the third experiment, published in December 1982 with Jean Dalibard and Roger, was the one that mattered most. This is the one Bell had been waiting for. Aspect replaced the fixed polarizers with acousto-optical switches, an ultrasonic standing wave in water driven at approximately 25 MHz, deflected photons between 2 differently oriented polarizers. The effective switching occurred at about 50 MHz, with complete orientation changes every 6.7 to 13.3 nanoseconds. The 2 switches were driven at slightly different frequencies by independent radio frequency generators, making the switching pattern quasi-random. Here are the numbers that matter. The distance between the 2 switches was 13 meters. Light takes approximately 40 to 43 nanoseconds to travel that distance. The switching intervals were 6.7 to 13.3 nanoseconds. The photon emission delay was about 5 nanoseconds. Both of these timescales are small compared to the light travel time. A detection event on one side and the corresponding setting change on the other side was separated by a space-like interval. No signal traveling at the speed of light or slower could have carried information between them. For the first time in history, the polarizer settings were changed while the photons were in flight. I need to explain why this matters so much, because the concept of space-like separation is the hinge on which the entire argument turns. In special relativity, 2 events are space-like separated if no signal traveling at or below the speed of light can connect them. They are too far apart in space and too close together in time for any causal influence to pass between them. If the detection event at detector A and the setting choice at detector B are space-like separated, then there is no physical mechanism consistent with special relativity by which the setting at B could have influenced the outcome at A, or vice versa. This is not a practical limitation about current technology. It is a fundamental constraint of space-time geometry. Nothing, no signal, no wave, no field, no information of any kind can travel between space-like separated events. And yet, the correlations are there. That is the core of the mystery. The universe produces correlations between events that cannot have communicated with each other. Not that we do not know how they communicated. That communication is geometrically impossible given the structure of space-time. The experiment was enormously difficult. Beam sizes had to be cut by a factor of 3 to fit the switch aperture, which destroyed the coincidence rates. True coincidence rates dropped to just a few per second, with accidental coincidences at about 1 per second. Data collection required 8,000 seconds for the Bell test, and another 16,000 seconds for auxiliary measurements. The result was a violation by 5 standard deviations. Quantum mechanics predicted 0.112. Aspect measured 0.101, plus or minus 0.020. Agreement within error bars. The locality loophole was for all practical purposes closed. There was no way a signal traveling at light speed could have coordinated the two detectors. The universe had been asked, under the strictest conditions ever imposed, whether it was locally real, and it had answered, it is not. Now, what happened next is the part of this story that I find most damning, and it has nothing to do with physics. Aspect had produced the most profound experimental result since the discovery of quantum mechanics itself. He had shown that the universe violates local realism, that the picture of reality that had guided physics since Newton, that objects have definite properties and can only be influenced by their immediate surroundings, is false. This should have been front-page news. It should have triggered an intellectual earthquake. It should have forced the entire physics community to stop and ask, what is reality actually made of? It did not. The response was overwhelmingly indifference. Aspect himself described it years later in his Nobel podcast. Mostly nobody cared, he said, for several good reasons. The most important reason is that it was only about interpretation. If you are a young physicist, active, you use quantum mechanics. It works. Why would you care about an epistemological debate between these two old glories? The Nobel Scientific Background document for the 2022 prize confirms this assessment with remarkable frankness. Some people said, well, this is really weird, but dismissed that thought because the status quo already held that quantum mechanics is strange. The inclination of the research community at the time was to just carry on using quantum mechanics and not worry about what it meant. And this was not just passive indifference, it was actively enforced. There is a famous story about a conference on quantum foundations at Eris, Sicily in 1985. The conference organizer invited John Bell to give the opening lecture. Several senior physicists objected, not because they disagreed with Bell's theorem, the math is not controversial, but because they believed the topic was inappropriate for a serious physics conference. Foundations was philosophy. Philosophy was not physics. The fact that the most mathematically precise result in the foundations of physics was being dismissed as not physics tells you everything about the pathology of the culture. John Clauser described the culture in even more devastating terms. A severe stigma, he said, began to develop within the physics community towards anyone who sacrilegiously was critical of quantum theory's fundamentals. Any physicist who openly criticized or even seriously questioned these foundations was immediately branded as a quack. There remained alive a minority of the theory's founders, notably Einstein, Schrödinger, and de Broglie, who were still critical. These men were obviously not quacks. They all had Nobel Prizes. Instead, gossip among physicists branded these men senile. I want you to sit with that for a moment. The profession's defense mechanism against uncomfortable questions was to declare that the people asking them, including 3 of the greatest physicists who ever lived, were mentally declining. The dismissal was not intellectual, it was personal, and it worked for decades. And so the most important experimental result in the foundations of physics was published, verified, and then quietly filed away. The establishment acknowledged the data and then turned back to their accelerators and condensed matter systems and string theories. The result sat in the literature like a loaded gun that nobody wanted to pick up. The transformation only came in the 1990s, and the reason was money. In 1991, Arthur Eckert published a quantum key distribution protocol, E91, based directly on Bell's theorem. The security of the encryption was guaranteed by the violation of Bell's inequality. If an eavesdropper intercepted the photons, the Bell violations would disappear. The key would be compromised and the parties would know. Suddenly, entanglement was worth something. Peter Shor published his quantum factoring algorithm in 1994, threatening every RSA encryption system on Earth. Zeilinger's group demonstrated quantum teleportation in 1997. The quantum information revolution was underway, and every piece of it traced back to Bell's 1964 paper in that dead journal. The stigma dissolved almost overnight. The thing that had been career poison for 3 decades became the hottest field in physics. But the loopholes, thin as they were, kept the fundamental question technically open. And over the next 33 years, experimentalists would seal every one of them. The result did not get better. It got worse. The violations got stronger. The statistics became more crushing, and the auctions for saving local realism got fewer and more desperate. There were 2 major loopholes left after Aspect's experiments, and for decades, defenders of local realism clung to them the way a man clings to a ledge over a canyon. The first was the detection efficiency loophole. Only a tiny fraction of the entangled photon pairs produced in Aspect's experiment were actually detected. The overall detection efficiency was around 0.01%. To make the Bell test work, you had to assume that the detected pairs were representative of all pairs. But what if nature was being selective? What if the pairs that happened to be detected were systematically different from the pairs that were lost? This is called the fair sampling assumption, and violating it is not as crazy as it sounds. Imagine you are polling voters, but your polling method only reaches voters who answered their phones on weekday afternoons. You might get a skewed result, not because voters overall lean one way, but because the voters you can reach are not representative. The detection efficiency loophole is the same idea applied to photons. If the photons you detect are a biased sample, you could see a Bell violation in your data, even though the full population of photon pairs obeys Bell's inequality perfectly. A sufficiently clever local hidden variable model could exploit the undetected events to fake a violation. Philip Pearl demonstrated this with an explicit model in 1970, and Arthur Fine extended the analysis. The mathematics showed that to close this loophole, using the CHSH inequality, you needed detection efficiency above 82.8%. With a different inequality, Eberhard's version, and partially entangled states, the threshold dropped to about 66.7%. In 1982, nobody was anywhere close to either number. The second was the locality loophole, which Aspect had addressed, but not fully closed. His acousto-optical switches were periodic, not truly random. They oscillated at fixed frequencies. In principle, a sufficiently clever hidden variable model could predict the switching pattern and coordinate the results. What was needed was genuine randomness in the setting choices, generated at the last possible moment with truly space-like separation between the choice event and the distant detection event. These loopholes were real, but I want to be clear about something. The physicists defending local realism by appealing to these loopholes were engaged in a retreat, not an advance. They were not proposing specific mechanisms that exploited the detection inefficiency. They were not explaining how the periodic switches could actually be predicted by hidden variables. They were pointing to the logical possibility that such mechanisms could exist without producing any evidence that they did. It was the physics equivalent of a defense attorney saying my client could theoretically have been framed without offering a single reason to believe framing actually occurred. The burden of proof had shifted. Quantum mechanics was producing exact predictions confirmed by experiment. Local realism was producing excuses, but science demands that loopholes be closed, and so a generation of experimentalists set out to close them. The locality loophole was properly addressed in 1998 by a team led by Gregor Weiss and Anton Zeivinger at the University of Innsbruck. They separated their detectors by 400 meters, used quantum random number generators to choose settings with true quantum randomness at the last possible moment, and measured a CHSH violation exceeding 30 standard deviations. The detection loophole was first closed in a different kind of system, trapped ions, by Rowe and collaborators in 2001, but closing both loopholes simultaneously in a single experiment. That took until 2015. And what happened in 2015 is the part where the last escape routes for local realism were welded shut. 3 independent groups on 3 different continents, using 3 completely different experimental techniques, all published loophole-free Bell tests within weeks of each other. The physics community sometimes calls this the year the question was settled, although, as I have been trying to explain, settling the experimental question just opens the interpretive crisis wider. I want to walk through each experiment because the technical ingenuity is extraordinary, and because the combined weight of these 3 results is the most definitive statement physics has ever made about anything. Not the most definitive statement about quantum mechanics, the most definitive statement about anything. The p-value of the Vienna experiment, 10 to the negative 31, is more certain than any measurement in the history of particle physics, more certain than the Higgs discovery, more certain than the measured value of the electron's magnetic moment, more certain than virtually any other experimental result you can name. That is how dead local realism is. The first was the Delft experiment, published on October 21, 2015, in Nature, led by Ronald Hansen at the Delft University of Technology in the Netherlands. The setup was radically different from every previous Bell test. Instead of photons, Hansen used nitrogen vacancy centers in diamond, which are defects in the diamond crystal lattice that behave like tiny quantum systems with electron spins that can be controlled and read out with extraordinary precision. 2 of these diamond chips were placed in separate laboratories, 1.3 kilometers apart, connected by a dark fiber optic cable running under the Delft campus. Entanglement was established through entanglement swapping. Each nitrogen vacancy center was first entangled with a photon, with about a 3% success rate. The photons were sent to a central station for a joint measurement. If it succeeded, the two distant electron spins became entangled, even though they had never directly interacted. The success rate was punishing. Approximately 1 in 156 million attempts produced a usable entangled pair, about 1 valid trial per hour. Over 220 hours, across 18 days, the team accumulated 245 valid trials. The CHSH parameter was S equals 2.42 plus or minus 0.20, with a p-value of 0.039. The detection loophole was closed, because once entanglement was heralded by the central station, the electron spins could be read out with near-perfect efficiency. The locality loophole was closed by the 1.3 kilometer separation and fast quantum random number generators. The second was the Vienna experiment, published on December 16, 2015, in Physical Review Letters, led by Anton Zeilinger and first author Marissa Gustina at the University of Vienna. Entangled photon pairs from spontaneous parametric down conversion, detected by transition edge sensors, developed at NIST with intrinsic detection efficiency greater than 98%. The system heralding efficiency was at least 75%, well above the Eberhard threshold. The detectors were placed 60 meters apart in the sub-basement of the Hofburg Castle in Vienna, which, in terms of dramatic settings for an experiment about the fundamental nature of reality, is hard to beat. The result was a p-value of less than or equal to 3.74 times 10 to the negative 31. That is not a typo. 10 to the negative 31, that is an 11.5 standard deviation violation. To give you a sense of how definitive that is, the odds of this result occurring by chance under local realism are less than 1 in a million, trillion. The experiment collected thousands of trials per second, sufficient data in under an hour. The third was the NIST experiment, published the same day in the same journal, led by Lyndon Christa Schaum at the National Institute of Standards and Technology in Boulder, Colorado. Entangled photons at telecom wavelengths, around 1550 nanometers, detected by superconducting nanowire single photon detectors with greater than 90% efficiency. Detectors 184 meters apart. Light-speed communication time between them was 617 nanoseconds. Measurements were completed more than 40 nanoseconds before any signal could have arrived from the other side. The p-value was 5.9 times 10 to the negative 9, greater than 6 sigma. And here is a detail I genuinely love about this experiment. The random number generators combined quantum randomness sources with predetermined pseudorandom bits extracted from the scripts of Back to the Future, Star Trek, Monty Python and the Holy Grail, Saved by the Bell, and Doctor Who. The experiment that helped seal the fate of local realism used random numbers generated by Monty Python. 3 experiments, 3 different technologies, 3 different continents, 1 answer. The universe is not locally real. And then they went after the last remaining loophole, the freedom of choice loophole. The idea that maybe the random number generators were not really random. Maybe the detector settings and the hidden variables shared some common cause deep in the past, some cosmic conspiracy that coordinated the entire experiment from the beginning. In February 2017, a collaboration including Zeilinger, David Kaiser at MIT, and Alan Guth at MIT published results from a cosmic bell test. Instead of laboratory random number generators, They used light from Milky Way stars, approximately 600 light-years away. The color of each incoming stellar photon, red or blue, determined the measurement setting. The Bell inequality was violated by more than 7 sigma and 11 sigma in 2 separate configurations. Any hidden common cause coordinating the settings and outcomes would have to have been established at least 600 years ago, before the starlight was emitted. Then, on January 11th, 2018, at the Observatorio del Roque de los Muchachos on La Palma in the Canary Islands, they went further. The Telescopio Nazionale Galileo, with its 3.58-meter mirror, was pointed at one high redshift quasar. The William Herschel telescope, with its 4.2-meter mirror, was pointed at a different quasar in the opposite direction of the sky. The light from these quasars was emitted 7.8 billion and 12.2 billion years ago. That light, billions of years old, was used to choose the detector settings in real time. I want you to appreciate the sheer ambition of this. They used the oldest light available to the human species as a random number generator. The photons that chose the detector settings had been traveling through space since before the Earth existed, before the Sun formed, before our galaxy had finished assembling itself. If there is some cosmic conspiracy rigging the experiment, it would have had to be set in motion when the universe was a fraction of its current age. The experimenters were literally reaching back through cosmological time to ensure their choices were free. Over 30,000 entangled photon pairs were measured. The Bell inequality was violated by 9.3 sigma. The p-value was less than 7.4 times 10 to the negative 21. This excluded any local realist influence mechanism from 96% of the space-time volume of the past light cone of the experiment, from the Big Bang to the present. If there is a conspiracy, it was established within the first 4% of the age of the universe, less than 600 million years after everything began. And in May of 2018, the results of the Big Bell test were published in Nature. Approximately 100,000 human volunteers across the world played an online video game designed to produce genuinely unpredictable binary choices. A machine learning oracle tried to predict each player's next input, incentivizing truly random behavior. The participants generated over 97 million binary choices in 12 hours on November 30th, 2016. Those choices were routed in real time to 13 different experiments on 5 continents using photons, atoms, atomic ensembles, and superconducting devices. All 13 experiments violated Bell's inequality. Greater than 8 standard deviations. 100,000 humans actively trying to be unpredictable, freely choosing in real time, and the universe still refused to be local and real. Before I move forward, there is something I need to tell you about John Bell, because the timing of what happened next is the part of this story that I find hardest to accept. On October 1st, 1990, John Stuart Bell suffered a cerebral hemorrhage at CERN. He died the same day. He was 62 years old. According to multiple credible sources, including the Mac Tutor History of Mathematics archive at St. Andrews and Physics World magazine, Bell had been nominated for the Nobel Prize that year. Nobel nomination records are sealed for 50 years, so the 1990 records will not be public until 2040. The claim cannot be formally verified, but the pattern of major awards Bell received in his final years, the Hughes Medal from the Royal Society, the Dirac Medal, the Heinemann Prize, honorary degrees from Queen's University Belfast and Trinity College Dublin, all suggest the establishment had finally caught up to the magnitude of his work. He died weeks before what many in the physics community believed would have been his Nobel year. His final published paper, Against Measurement, had appeared in Physics World in August of that year, just weeks before his death. It was a characteristically aggressive critique of the use of measurement as a fundamental term in quantum mechanics. He was challenging the profession's sacred cow with his last breath. That was Bell. He could not stop pulling at threads, even when nobody wanted to see what unraveled. His wife Mary, also a physicist at CERN, survived him. He was an atheist, a long-term vegetarian. In his version of Schrödinger's cat, he replaced the alive and dead states with hungry and not hungry because he did not want to think about killing cats, even hypothetical ones. Roman Jacques, who worked with him on the chiral anomaly, described his overwhelming intellectual precision and honesty. He retained his Belfast accent his entire life. Stuart Friedman, the graduate student who co-performed the first Bell test with Clauser, died on November 10, 2012, at age 68, a decade before the Nobel. The prize was finally awarded on October 4, 2022, to Alain, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Clauser was 80 years old. Aspect was 75. At the ceremony, Aspect spoke first. His words were precise. That recognition should go first to the late John Stuart Bell, without whom we would not be here today. He told the permanent position story to the Nobel audience. 40 years. The experiment was performed in 1982. The prize came in 2022, and the man who made it all possible was in the ground for 32 of those years. But this story is not just about the people, though the human cost is real, and it is inexcusable. This is about what the result means, because now the loopholes are closed. The detection efficiency is above threshold. The separation is space-like. The settings were chosen by quasar light from before the Earth formed. Every escape route for local realism has been sealed by experiment, which means you are now standing in front of 4 doors, and you have to walk through one of them. And I need you to understand that none of them lead back to the world you thought you lived in. This is the part most popular accounts of Bell's theorem get wrong, and it is a misconception I want to correct before we go any further, because it changes everything about how you understand the result. You have probably heard, maybe even on this channel in previous videos, that Bell proved the universe is non-local. That is not what Bell proved. Bell proved that the universe is not locally real. Those sound similar. They are not. Not locally real is a conjunction. It means the combination of locality and realism fails. You can sacrifice locality. You can sacrifice realism. You can sacrifice both. You can sacrifice something else entirely. The common framing collapses a 3-way crisis into a 1-way street, and it hides the real horror, which is that every exit leads somewhere terrible. Let me walk you through the 4 doors. I am going to give each one the time it deserves, because the details matter and because the differences between them are not academic distinctions. They are fundamentally different pictures of what reality is. And you have to pick one. Door 1. Give up locality. Accept that the universe communicates instantaneously across any distance. This is the option Bell himself preferred through Bohm's pilot wave theory. The idea is that particles do have definite properties at all times, but measuring one particle instantaneously affects the physical state of a distant, entangled partner. The non-locality is real. The connection is real. Something links them that does not respect the speed of light. And let me be clear about what instantaneously means here, because it is easy to understate. It does not mean very fast. It does not mean approaching the speed of light. It means literally zero delay. In Aspect's third experiment, the switching events and the detection events were space-like separated. No signal traveling at the speed of light could connect them, but the correlations were still there. In the 2018 Cosmic Bell test, the measurement settings were determined by photons that had been traveling through space for 12 billion years. The correlations were still there. Whatever connects entangled particles, it does not care about distance, not about meters, not about kilometers, not about billions of light years. The correlation between two entangled photons measured on opposite sides of the observable universe would be exactly the same as the correlation between two photons measured on the same table. The universe does not dilute this connection with distance. It does not weaken it. It does not delay it. It simply is. Now, before you object that this violates special relativity, it does not, or at least it does not in any way you can exploit. The no communication theorem, proven rigorously within quantum mechanics, shows that you cannot use entanglement to send information faster than light. Here is why. When Alice measures her half of an entangled pair, she gets a random result, +1 or -1, 50-50, completely unpredictable. Bob, measuring his half, also gets a random result, 50-50. Neither Alice nor Bob can tell from their own results alone that anything has happened on the other side. The non-locality only becomes visible when they compare their results afterward, using classical communication that travels at or below light speed. Bob's local statistics are always perfectly random regardless of what Alice does. His reduced density matrix does not change. The physicist John Jarrett decomposed Bell's locality conditions into two independent conditions in 1984. Parameter independence says Alice's outcome probability does not depend on Bob's choice of measurement setting. Outcome independence says that given the hidden state and both settings, Alice's outcome does not depend on Bob's specific result. Standard quantum mechanics violates outcome independence while preserving parameter independence. Bohm's theory does it the other way around, but in both cases, the violation cannot be used for signaling because you would need to know the hidden state to exploit it, and the hidden state is precisely what you do not have access to. What this means practically is that the non-locality is hidden in the correlations. It is invisible to either party individually. It only becomes visible when you bring the results together. It is as if the universe is whispering a secret to itself, and you can only hear it if you compare notes from both sides. Neither side alone hears anything unusual. Abner Shimony called this passion at a distance, rather than action at a distance. But the price of door one is steep. In Bohm's pilot wave theory, the wave function is a real physical object, not a mathematical convenience, not a calculation tool, a thing that exists. And it exists not in ordinary three-dimensional space, but in configuration space, a space with 3n dimensions where n is the number of particles in the universe. For a universe with approximately 10 to the 80th particles, that is a wave function living in a space with roughly 10 to the 80th dimensions. Every particle in the universe is connected to every other particle through this wave function, and the connection is instantaneous. The apparent separateness of the world, the feeling that this table is here and that star is over there, and they have nothing to do with each other, is an illusion generated by the fact that you only see a three-dimensional shadow of a reality with more dimensions than atoms. The cost of keeping particles real and definite is accepting that everything in the universe is connected to everything else in a space you cannot see, through a wave you cannot directly detect, with correlations that propagate in zero time. Bell accepted this cost. He thought it was the most honest option. He said on multiple occasions that the pilot wave theory was the only interpretation that took quantum mechanics seriously, as a description of reality rather than hiding behind words like complementarity and measurement. I respect that position, even though I am not sure it is the right one. There is another cost that rarely gets discussed. In Bohm's theory, the pilot wave determines the velocity of each particle based on the configuration of all particles. This means that if you perturb one particle, even slightly, you change the pilot wave, which changes the velocities of all other particles everywhere, instantly. The universe, in Bohm's picture, is not a collection of independent things. It is a single, indivisible, interconnected whole. The apparent separateness of objects is an illusion. Everything is correlated with everything else through the pilot wave, and the correlations are not mediated by any signal. They just are. The philosopher of physics Tim Maudlin has argued that this should not be called non-locality in the relativistic sense because there is no signaling, but it is certainly non-locality in the ordinary English sense. Things that are far apart are not independent, period. Door 2. Give up realism. Accept that particles do not have definite properties until you measure them. This is the Copenhagen interpretation, which is still the default position in most physics textbooks. The idea is that the wave function is not a description of a real thing out there in the world. It is a tool for calculating probabilities of measurement outcomes. Before you measure a photon's polarization, the photon does not have a polarization. It is not that you do not know the polarization. It is that there is no polarization to know. The property does not exist until the measurement creates it. Einstein hated this. His challenge to Abraham Pais captures it perfectly. Walking together at Princeton one evening, Einstein stopped and asked, "Do you really believe the moon exists only when you look at it?" Pais recorded the exchange in his biography. The question was not rhetorical. Einstein was genuinely asking whether the Copenhagen interpretation required him to accept that macroscopic objects have no definite properties when unobserved. The Copenhagen answer, strictly interpreted, is yes. Or more precisely, the question is meaningless. You cannot ask about properties independent of measurement context. The moon exists when you look, because looking is all there is. The concept of the moon existing when nobody is looking is not false. It is undefined. The price of door 2 is that reality is not there when you are not looking at it. Not in the sense that it might not be there, in the sense that the word there loses its meaning. The universe does not contain objects with properties. It contains potentialities that become actual only upon interaction. And the boundary between the quantum world of potentialities and the classical world of definite outcomes, what Bell called the shifty split, has never been satisfactorily defined. Let me make this tangible. You are sitting somewhere right now, and there is a chair or a couch or a bed beneath you. You believe it has a definite shape, a definite position, a definite mass, whether or not you are observing it. You believe that if you left the room and came back, the chair would still be there, in the same place, with the same properties. This belief is so fundamental to your experience that questioning it feels absurd. The Copenhagen interpretation says this belief, applied rigorously at the quantum level, is wrong. The photon in aspects experiment does not have a polarization before measurement. The electron in the Delft experiment does not have a spin direction before it is read out. And there is no sharp line, no defined boundary, no agreed upon scale at which the quantum rules stop applying and the classical rules take over. The chair is made of atoms. The atoms are made of electrons and nuclei. The electrons and nuclei obey quantum mechanics. At what point in the chain from electron to chair does definite reality emerge? Copenhagen has no answer. It has a shrug. Bell spent the last years of his life attacking this point. His against measurement paper argued forcefully that the word measurement should not appear in any fundamental formulation of physics. It is too vague, too human-centered, too dependent on an undefined boundary between observer and observed. If quantum mechanics tells you that properties do not exist until measured, then it needs to define what counts as a measurement. Does a Geiger counter count? Does a camera? Does a bacterium interacting with a photon? Does a single atom bumping into another atom? The standard modern answer is decoherence, the process by which quantum superpositions become entangled with their environment and effectively become classical. But decoherence does not solve the measurement problem. It explains why you do not see superpositions in practice. It does not explain why there is a single definite outcome at all. It moves the boundary. It does not eliminate it. If physics needs the word measurement to function, Bell argued, then physics does not understand what it is describing. And the fact that Bell made this argument in his final published work, knowing he was challenging the profession's most sacred cow, knowing it would not make him popular, tells you something about the kind of intellectual honesty the man possessed. He could have spent his later years accepting awards and giving comfortable lectures. Instead, he published a paper calling out the foundations of the standard interpretation. That was who he was. Door 3. Give up the uniqueness of outcomes. Accept the many worlds interpretation. This one was proposed by Hugh Everett III as his PhD thesis at Princeton in 1957. His advisor was John Archibald Wheeler. The idea is elegant in its brutality. There is no collapse of the wave function. There is no measurement problem. The Schrödinger equation applies universally, always, to everything without exception. When you measure a photon's polarization and get vertical, there is another branch of the universal wave function where you got horizontal. Both outcomes happen. Both versions of you are real. They simply cannot communicate because the branches decohere, becoming orthogonal in the wave function, unable to interfere. Many worlds preserves locality in a technical sense. The Schrödinger equation is a local equation. No superluminal signals are needed because the Bell correlations are explained not by communication between distant detectors, but by the branching of the universal wave function. Both outcomes occur at both detectors, and the correlation is a feature of which branches match up, not a signal sent between them. A 2019 analysis made this precise. It showed that Bell's theorem rests on 3 axioms: local causality, no superdeterminism, and one world. Accept the first 2, and you are logically compelled to accept many worlds. The price is obvious and extreme. An infinity of equally real universes an uncountable number of copies of you, diverging at every quantum event, every photon interaction, every radioactive decay. The universe you experience is one infinitesimally thin slice of an incomprehensibly vast multiverse. And the problem is not just philosophical, it is technical. The concept of probability becomes deeply problematic. If every outcome happens, what does it mean to say one outcome is more likely than another? This is the measurement problem of many worlds, and it remains unsolved despite decades of effort by some extremely clever people. The physics establishment's reaction to Everett's thesis was devastating, and I think this part of the story does not get told often enough. Wheeler, his own advisor, made him cut the thesis from 137 pages to a slim 27-page version that removed most of the philosophical implications. The full version was not published until decades later. Bohr's associate Leon Rosenfeld was actively hostile when Everett visited Copenhagen in 1959, hoping to discuss his ideas with Bohr directly. The reception was cold. Rosenfeld later described the many worlds interpretation as theology, which in physics is not a compliment. Everett never got an academic physics position, not because he could not do the work. His thesis advisor was John Archibald Wheeler, one of the most influential physicists of the 20th century. Everett was brilliant by any measure, but the culture of the profession had decided that thinking seriously about what quantum mechanics means was not real physics, and Everett's thesis was the most serious attempt to think about it that anyone had made in decades. He went into military operations research at the Pentagon's Weapons Systems Evaluation Group and later at the Institute for Defense Analyses. He became wealthy. He also became an alcoholic and a heavy smoker. He died of a heart attack on July 19, 1982, at the age of 51. His daughter Elizabeth, who struggled with mental illness including schizophrenia, took her own life on June 24, 1996. In her note, she expressed the hope of ending up in the same parallel universe as her father. His son, Mark Oliver Everett, who would become the lead singer of the band Eels, later said he did not know his father had been a famous physicist until the BBC made a documentary about many worlds in 2007. Mark described finding his father's body as a teenager and not understanding why he had spent his life drinking rather than doing physics. The answer, of course, is that the physics community told him his most important idea was not worth pursuing, which makes Everett's interpretation feel less like a theory and more like a haunting. The man who proposed that the universe splits into infinite copies was himself split apart by the profession's inability to take his idea seriously. Door 4. Give up free will. Accept superdeterminism. This is the escape route that almost nobody talks about, and it is the one that, when you understand it fully, should disturb you the most. The assumption in Bell's theorem that rarely gets examined is called measurement independence. It says that the experimenter's choice of what to measure is statistically independent of the hidden variables that determine the outcome. The experimenters are free to choose their detector settings, and those choices are not correlated with the properties of the particles being tested. Superdeterminism rejects this. It says that the settings of the detectors and the hidden variables of the particles were both determined by initial conditions at the beginning of the universe, and they are correlated, not by conspiracy, not by signal, by determinism. The universe is a clockwork mechanism in which every event, including your choice to rotate a polarizer to 22.5 degrees, including your choice to watch this video, including the specific neural firing pattern in your brain that constitutes the experience of making a choice, all of it was fixed at the moment of the Big Bang. And I want to make clear how radical this is, because the word determinism sounds almost reasonable when you say it quickly. You might think, well, maybe the universe is deterministic. Maybe classical physics was right about that part. But superdeterminism is not garden variety determinism. Ordinary determinism says the laws of physics determine what happens next, given what happened before. Superdeterminism says the initial conditions of the universe were arranged in such a way that every experimental test of Bell's inequality happens to produce exactly the correlations predicted by quantum mechanics, not because the universe is actually quantum mechanical, but because the initial conditions were fine-tuned to mimic quantum correlations for every possible experiment anyone could ever run, at every scale, at every location, for the entire history of the universe. The initial conditions had to know in some sense what experiments humans would perform 13.8 billion years later, and they had to be arranged to produce the right fake results for each one. That is not a physical mechanism. That is a conspiracy theory about the Big Bang. Bell coined the term superdeterminism in a 1985 BBC radio interview with Paul Davies. He said, "There is a way to escape the inference of superluminal speeds and spooky action at a distance, but it involves absolute determinism in the universe, the complete absence of free will." He then added, "Suppose the world is superdeterministic. Not only is what happens at one detector determined by the initial conditions of the universe, but what the experimenter does at that detector is also determined. In that case, the experimental result is no longer a fair sample of what would have happened under different conditions." Nobel laureate Gerard Hooft has advocated for this position through his cellular automaton interpretation of quantum mechanics. Published in 2016, he proposes that quantum mechanics arises from a deterministic cellular automaton operating at the Planck scale. Sabine Hossenfelder is the most vocal contemporary proponent, arguing in a 2020 paper in Frontiers in Physics that the standard objections to superdeterminism are ill-founded, and calling free will, in her words, logically incoherent nonsense. But here is why most physicists reject superdeterminism, and why I think they are right to reject it, at least until someone produces a compelling specific model. Superdeterminism does not just sacrifice free will, it sacrifices the entire enterprise of experimental science. If the settings of your detectors are correlated with the properties you are trying to measure, then no experiment can be trusted. You cannot test any theory because the universe might have arranged the initial conditions to produce misleading results. Shimony, Horn, and Clauser wrote in 1976, "Unless we proceed under the assumption that hidden conspiracies of this sort do not occur, we have abandoned in advance the whole enterprise of discovering the laws of nature by experimentation." Zeilinger added his own version. If measurement settings were determined in advance, then it would make no sense at all to ask nature questions in an experiment, since then nature could determine what our questions are. And the cosmic Bell tests push the superdeterministic correlation back to the limits of observational cosmology. The 2018 quasar experiment required any such correlation to have been established within the first 4% of the age of the universe, less than 600 million years after the Big Bang. If you want superdeterminism to explain Bell violations, you need a mechanism that correlated the initial conditions of quasars 12 billion light years apart with the experimental choices of physicists on Earth. in 2018. All of it set in motion before the first stars finished forming. And there is a final turn of the screw. In 2006, mathematicians John Conway and Simon Cochin published the free will theorem, using 3 axioms, one about quantum predictions for spin measurements, one about entangled particles, and one about the finite speed of information propagation. They proved that if experimenters have free will, meaning their choices are not determined by prior information available to the particles, then the particles' responses are also not determined. The particles, in a precise mathematical sense, have free will too. Conway reportedly said, "It is not about theories anymore. It is about what the universe does. A particle has a choice." Their strong free will theorem of 2009 weakened the assumptions even further. The implication is a symmetry. If you deny free will to the experimenter, you deny it to the particles. If you grant it to the particles, you grant it to the experimenter. You cannot selectively eliminate freedom from one side of the experiment. And there is a second misconception I need to correct here, because I see it everywhere and it drives me up the wall. Dozens of YouTube videos claim that the quantum eraser experiment proves retrocausality, that the future can change the past. They are wrong. The quantum eraser results are fully explainable by post-selection. When you look at the total pattern of detections without sorting by the idler photon outcomes, you see no interference pattern. The interference only appears when you sort the signal photons into subsets based on what happened to their partner photons. That sorting is a classical operation that happens after the fact. No information travels backward in time. The pattern was always there in the total data. You just cannot see it without the sorting key. The real case for retrocausality comes from a completely different direction, from the work of philosopher Hugh Price at Cambridge and physicist Ken Wharton at San Jose State. They argue that Bell violations should be understood not as evidence for nonlocality, but as evidence for time-symmetric hidden variable theories, in which future measurement settings genuinely constrain past hidden variable states. This is distinct from superdeterminism. It allows free will while permitting the future to influence the past. Price actually wrote to Bell about this in 1988. Bell wrote back that when he tried to think about backward causation, he lapsed quickly into fatalism. The retrocausality program is more interesting and more serious than it gets credit for, and I think it deserves a dedicated video of its own at some point. So those are your 4 doors: nonlocality, anti-realism, many worlds, superdeterminism. Each one requires you to give up something that feels essential to the way you think the world works. The separateness of distant objects, the existence of properties when unobserved, the uniqueness of your experience, the freedom of your will. I have spent a lot of time thinking about which door is the right one, and I will tell you what I have concluded. I do not know. Nobody knows. The experiments tell you that local realism is dead. They do not tell you which funeral to attend. Bell preferred Bohmian mechanics because at least it was honest about the price. He thought physicists had a moral obligation to be clear about what quantum mechanics demands, rather than hiding behind the vague language of complementarity and measurement. I find that persuasive, but I also find many worlds compelling for different reasons, and the retrocausality program is more rigorous than most people give it credit for. The point is not which interpretation is correct. The point is that every interpretation requires you to abandon something you thought was fundamental about reality. And if that does not unsettle you, you have not understood the result. And that brings me to where this story ends. or rather, where it refuses to end. The calculations have been checked. The experiments have been repeated hundreds of times across 4 decades. The loopholes have been closed one by one. The CHSH parameter is not 2. It has never been 2. It is 2.697 in Aspect's lab, 2.42 in Delft, and it has been pushed to the quantum mechanical maximum of 2.828 in optimized modern experiments. The cosmic Bell tests have used light from before the solar system existed. The Big Bell test used random choices from 100,000 human volunteers across 5 continents. Every result agrees. Local realism is violated. But before I let that conclusion sit, I need you to hear the human cost of this story one final time, because the science does not exist in isolation from the people who made it, and the way those people were treated tells you something important about how the profession handles truths it does not want to face. David Bohm, whose pilot wave theory sparked Bell's investigation, was driven from his country by McCarthyism. He had his passport confiscated. He lived as an exile for years in Brazil, then Israel, then England. He watched the physics establishment dismiss his life's work as artificial metaphysics, as superfluous, as something that should be agreed to be ignored. He discovered the Aharonov-Bohm effect, proving that electromagnetic potentials are physically real, and even that was initially met with skepticism. He died of a heart attack in a London taxi in 1992, at the age of 75. He was never awarded the Nobel Prize. He was never invited back into the mainstream. The theory he created, which Bell's work proved, was the honest version of quantum mechanics, is still taught in most departments as an oddity, a footnote, a curiosity rather than a foundational framework. John Stuart Bell worked on the most important problem in physics as a hobby, published the most important theorem in the history of science in a journal that ceased to exist, hid his foundational interests from his colleagues at CERN because the culture of his profession made the question toxic, and died of a cerebral hemorrhage at 62, weeks before what many in the community believed would have been his Nobel year. His wife Mary survived him. The theorem that bears his name now underpins a multi-billion-dollar technology industry. He never saw a cent of it. He never saw the recognition. He never lived to see the loophole-free tests that confirmed his prediction beyond any conceivable doubt. John Clauser performed the first experimental Bell test in a Berkeley basement, with no funding, using equipment he scrounged from other labs. He was rewarded by being thrown out of Feynman's office and told to go do real physics. He never held a tenured professorship. He waited 50 years for his Nobel Prize. He was 80 years old when he received the call, and he actually expected the experiment to prove quantum mechanics wrong. He wanted local realism to win. When the universe told him otherwise, he accepted it and published. That is scientific integrity at its purest, and the profession punished him for it. Alain Aspect was warned by Bell himself that a majority of physicists would consider him a crackpot. He spent 5 years building an experiment that the profession did not want, addressing a question the profession considered frivolous, using techniques the profession thought were a waste of time. The result was met with indifference. He waited 40 years for his prize. At the ceremony, his first words honored the dead man who made it all possible. Abner Shimony, the philosopher-physicist who co-derived the CHSH inequality, who helped make Bell's abstract theorem experimentally testable, who gave the entire field its mathematical framework, died in 2015. 7 years before the Nobel, he never received the call. Hugh Everett proposed the many worlds interpretation as a 26-year-old PhD student. The establishment's response was so hostile that he abandoned physics entirely. He went into military operations research, became an alcoholic, and died at 51. His daughter took her own life 4 years later. In her note, she hoped to reach the same parallel universe her father was in. Stuart Friedman, Claus's graduate student who co-performed the first Bell test, moved into nuclear and neutrino physics and became a respected figure in those fields. He died in 2012. A decade before, the Nobel recognized the work he helped make possible. That is the record. That is what the physics community did to the people who dared to ask what quantum mechanics means. And here is the final bitter irony that ties the entire story together. Bell's theorem, which was ignored as philosophy for decades, which was treated as professionally disreputable, which cost the people who worked on it their careers and their reputations, now underpins a multi-billion-dollar global industry. The quantum information revolution, quantum computing, quantum cryptography, quantum teleportation, quantum sensing, every piece of it traces directly to Bell's 1964 paper and to the experiments by Clauser, Aspect, and Zeilinger that confirmed it. Eckert's E91 protocol, which launched practical quantum cryptography, is based directly on Bell's inequality. The security guarantee is the violation itself. If an eavesdropper intercepts the photons, the Bell violations disappear, and the parties know the key is compromised. IBM, Google, IonQ, Quantinuum, PsiQuantum, the European Union's EuroQCI initiative, China's Quantum Satellite Network and its Mesius satellite, the US National Quantum Initiative, all of it, every last piece, rests on the entanglement that Bell proved cannot be explained away and that Aspect proved is real. The thing the profession called a distraction is now its most commercially valuable product. The people the profession punished are now the field's founding figures. The question the profession tried to suppress is now the question driving some of the most ambitious and expensive technology projects in human history. And the 2022 Nobel Prize recognized the experiments and the technology, but studiously avoided the interpretation. The citation said, "experiments with entangled photons," establishing the violation of Bell inequalities and pioneering quantum information science. Those last three words, quantum information science, are doing enormous work. The Nobel Committee recognized what you can do with entanglement. It did not address what entanglement tells you about reality. The committee's press release discussed qubits, quantum computing, quantum cryptography. It did not mention non-locality. It did not mention the measurement problem. It did not mention the fact that the experiments it was honoring had destroyed a 300-year-old picture of reality and left nothing agreed upon in its place. The profession has learned to profit from the phenomenon while continuing to avoid what it implies. Shut up and calculate, but now with venture capital and stock options. I think Bell would have had something sharp to say about this. He spent his life arguing that the measurement problem was not a philosophical curiosity, but a genuine crisis in the foundations of physics, and that pretending otherwise was intellectually dishonest. I think he would have been pleased that the experimentalists were finally recognized. I think he would have been exasperated that the recognition came framed as technology rather than as truth. But I think he would also have smiled that Belfast accent smile because the theorem had won. The data was in. The question he asked could no longer be avoided. It could only be deferred. And deferral has a shelf life. I think about Bell a lot when I am working on these scripts. The quiet stubbornness of him, the willingness to pursue a question that nobody else thought mattered. In his spare time, during holidays, in a dead journal, knowing that his colleagues would not care and might actively disapprove. There is a tendency in how we tell the stories of great scientists to make them sound like lone geniuses who were recognized in their time. Bell was not recognized in his time. He was ignored. He was marginalized. And he kept working on the question anyway, not because it would advance his career, but because he could not stop thinking about it, because the question would not let him go. The question was this: what is reality actually doing when you are not looking at it? He proved that whatever reality is doing, it is not what we thought. The universe is not a collection of separate objects with definite properties influencing each other only through local interactions. That picture, the picture Newton gave us, the picture Einstein wanted to save, the picture that feels obvious and natural and correct every moment of every day, is wrong. Not approximately wrong. Not wrong in some exotic regime of extremely small particles or extremely high energies. Wrong in principle. Wrong at every scale. Wrong for every particle. The entangled photons in Aspect's lab do not respect locality any more than the entangled ions in Rowe's trap, any more than the entangled nitrogen vacancy centers in Hansen's diamonds a kilometer and a third apart. The violation is the same everywhere. The universe does not become locally real when you zoom out. It was never locally real to begin with. And this is not something that only applies to carefully prepared laboratory states. Entanglement is not rare. It is not fragile. It is not confined to physics experiments. Entanglement is everywhere. Every interaction between any two quantum systems produces it. Every photon that bounces off your skin and reaches someone's eye creates entanglement between you and the photon. Every breath you take entangles the molecules of air with the molecules of your lungs. The reason you do not notice this in daily life is not that entanglement is absent. It is that decoherence, the interaction with the environment, scrambles the quantum correlations so rapidly that they become undetectable. But undetectable is not the same as non-existent. The universe is saturated with entanglement. The correlations are everywhere. The violation of local realism is not a laboratory curiosity. It is the default condition of all matter at all times, at all scales. You are living in a universe that is not locally real, and you always have been. And the only reason it feels locally real to you is that your senses are too coarse to detect the entanglement that permeates everything. That is what Aspect measured in 1982. Not an exotic quantum phenomenon, the fundamental character of reality, stripped of the decoherence that usually hides it from view. The experiments have narrowed the options to 4, and all 4 are worse than not knowing. The universe either talks to itself instantly across any distance, through connections that span a space with more dimensions than there are atoms, or it does not exist when you are not looking at it, and the word exist loses its meaning between observations, or it splits into an infinity of equally real copies every time anything happens, and the you reading this sentence is one of an uncountable number of yous who are reading slightly different sentences in slightly different branches. Or it has been determining your every thought and action since the Big Bang. And the experience of free will is an illusion so complete that even the experiments designed to test it were predetermined to produce exactly the results they produced. There is no fifth option. The mathematics does not allow one. The experiments do not suggest one. You are stuck with these four, and you have been stuck with them since a working-class kid from Belfast, who could not afford grammar school, whose mother sewed his academic gown from blackout curtains, who hid his most important work from his colleagues, who published in a dead journal and died before the world caught up, proved it during his holidays. Bell once said something in an interview that I think captures the essence of his contribution better than any technical description. He said, "The founding fathers of quantum mechanics rather prided themselves that they had disposed of all questions of principle and were quite willing to go ahead with the practical problems of physics. I felt that there were certain questions of principle, and I was quite sure that these were of interest, and one day they would be of general interest. One day." He was right. It just took 40 years and his own death for one day to arrive. The number is 2.697. 40 standard deviations above the limit that local realism was supposed to obey, confirmed by every experiment performed in the 43 years since, confirmed by transition edge sensors in the sub-basement of the Hofburg Castle, confirmed by nitrogen vacancy centers in Diamond 1.3 kilometers apart, confirmed by quasar light 12.2 billion years old, confirmed by 97 million free choices from 100,000 human beings on 5 continents. The number has not moved. It will not move. The universe made up its mind about this a long time ago. We are just now, finally, reluctantly, starting to listen to what it has been telling us. The universe is not locally real. That is not a theory. That is not a hypothesis. That is not an interpretation. That is what the data says. It has been saying it since 1982, and you were never told what it means.